In this video, we are going to discuss about boundary conditions of electric field. On completion of this boundary conditions of electric field, students will able to identify the electrostatic boundary value problems by applying this Poisson's and Laplace equations. So in boundary conditions, whenever an electric field passes from one medium to other medium, this boundary occurs. So this boundary occurs between the two media. That is the condition which is existing between the boundary of these two media. Whenever this electric field is passing from one medium to other medium, we call that it as boundary condition. So here, depending upon the nature of this medium, we are dividing into two forms, that is boundary between conductor and free space, as well as boundary between two dielectrics with different properties. So this free space we will be saying it is nothing but it is a dielectric, which in the case we will be saying that is a boundary between the conductor and the dielectric. So for this boundary conditions we are applying the Maxwell's equation. So we can write that equation as closed integral of E vector dot dl vector equal to 0 and closed integral of d vector dot ds vector equal to q. So this electric field intensity we are decomposing into two components. One is tangential to the boundary and another one is normal to the boundary. So we are representing this as E vector is equal to E tan vector plus E normal vector. So in the boundary conditions of the electric field, here we are considering the boundary that is present between the conductor and the free space. So here the conductor we are taking as a infinite conductivity. So we can say some of the examples, that is copper or silver, we can take it as a conductor which is a good electricity. And here this field intensity which we are present inside this conductor is 0. So this electric field is 0, so that the flux density which is present inside the conductor is also 0. So no charge will exist between this conductor, and the charge which appears on the surface also will be equal to 0. Finally, the charge density within the conductor will be also 0, and the electric field, electric flux density and charge density which is present inside the conductor will be 0. So for determining this boundary conditions, we are using the closed path and the Gaussian surface here. So in the diagram it is clearly shown that we are considering the conductor along the free space of boundary. So here first one is electric field at the boundary. So in the electric field at the boundary, we are resolving into two components. One is tangential to the surface and another one is normal to the surface. So we can write this equation as closed integral of E vector dot dl vector equal to 0. So here we are considering a rectangular closed path. So we can write this equation as closed integral of E vector dot dl vector equal to integral of a to b E vector dot dl vector plus integral of b to c E vector dot dl vector plus integral c to d E vector dot dl vector plus integral d to a E vector dot dl vector equal to 0. So here we will be considering the portion that is C to D conductor which is present inside the conductor. So we are considering the electric field along that component as 0. So we can neglect that part and we can write the remaining part. So we can write it as integral of a to b E vector dot dl vector plus integral b to c E vector dot dl vector plus integral d to a E vector dot dl vector equal to 0. And here we are considering the width that is very small, so that is present along the distance that is a to b and c to d. So the width we are considering as del w. So we can rechange the equation as integral a to b E vector dot dl vector is equal to E vector of del w. And here this del w is present along the tangential direction. So we can write this equation as E vector is equal to E tan vector. And the portion which we have seen in the diagram, that is B to C region, which is parallel to the normal component. So we are considering the vector E vector is equal to En vector. So we can write it as integral b to c E vector dot dl vector equal to En of b to c dl vector. And the component that is b to c, in that b to 2 region will is the free space and the 2 to qz in the conductor. So whatever the region which is present in the conductive region, it is equal to 0. So we will be writing the equation as E vector is equal to 0. And here finally we can write that tangential component of this electric field intensity is 0 at the boundary, that is between the conductor and the free space. So we can say the electric field at the boundary between the conductor and free space is always the direction which is perpendicular to the boundary. So we can represent this equation as d tan is equal to epsilon naught into E tan equal to 0. That is tangential component of this electric flux density is 0 at the boundary which is present between the conductor and the free space. And the next one is dn vector at the boundary. So here to find this normal component, we are selecting a closed Gaussian surface which we are taking in the form of right circle of cylinder. So here its height is del h. So we are representing the half the part as del h by 2 in free space. So we can write this equation as, based on the Gauss law, closed integral of d vector dot ds vector is equal to q. So here we are dividing this surface integral into three surfaces. One is top, second one is bottom, and third one is lateral. So we can write this equation as integral of d vector dot ds vector at the top side plus bottom side plus lateral side is equal to charge which is present along the surface. And here this bottom surface which is in the conductive region, so we know that electric flux density will be 0 here and the total integral will be also 0. So we are considering only the top as well as the lateral surface here. So here the height is del h by 2. So we can write the equation as integral of d vector dot ds vector is equal to dn of integral top ds vector. So we can write it as dn into del s. So finally we can find out the equation, that is dn is equal to rho s. So the flux which is leaving the surface normally and the normal component of this flux density is equal to this surface charge density. So we can write this equation as dn is equal to rho s. And finally we can write the equation that is related to the En vector is equal to rho s by epsilon naught. So the tangential component of this electric field is 0 and the surface of the conductor is an equipotential surface. So finally we can find out the potential difference along this path and we can write the equation as minus integral of E vector dot dl vector. Then this E vector is equal to E tan vector which is equal to 0. So the potential difference between these surfaces will be 0. So all the points which are present on the conductor surface will be at the same potential. So if you are seeing about the boundary conditions between the conductor and the dielectric, the free space with this dielectric we can write it as epsilon is equal to epsilon naught. So the boundary is between this conductor and the dielectric. So we can represent this as epsilon is equal to epsilon naught into epsilon r. So we can write the equation E tan equal to D tan equal to 0, that is dn is equal to rho s and En is equal to rho s by epsilon naught into epsilon r. And the quiz questions on boundary condition of this electric field is, what will be the charge within the conductor, that is 0. Which component of the electric field intensity is always continuous at the boundary, that is tangential component, and the normal component of which quantity is always discontinuous at the boundary, that is electric flux density. Thank you.